You know how you get an update for the software on your phone? You start with version 1, you find some bugs, you release a patch, and eventually you get a whole new operating system. Well, believe it or not, our understanding of the atom has gone through almost the exact same process. It wasn't just discovered one day. It's an idea that has been tweaked, patched, and totally upgraded over time.
It all started with this one simple question. What if everything, and I mean everything, was made of the same tiny, invisible building blocks? It sounds simple, right? But that one question is the key to understanding the air we breathe, the ground we walk on, and even the device you're watching this on. So let's trace the journey of this incredible idea, from a simple guess to the complex model we have today. So, here's our game plan. First, we'll meet the original, simple idea of the atom. Then, we'll see how scientists found bug reports that started to show its flaws. We'll watch the modern atom make its grand entrance, tackle the mind-bending problem of how to weigh something so small, and finally, see how we landed on the ultimate standard we use today. Let's get started. All right, our story kicks off in the early 1800s with a brilliant scientist named John Dalton. Now, people had been talking about atoms for ages, going all the way back to the ancient Greeks. But Dalton, he was the first one to come up with a real scientific theory about them. He was trying to explain the whole world with just one big idea.
And this was his model. It's so beautifully simple. He imagined atoms as these tiny, solid, indestructible marbles, the ultimate Lego brick of the universe. In his mind, you couldn't break them, you couldn't destroy them, and an atom was the absolute smallest you could get. For a while, this theory explained a lot. But while science doesn't like to sit still,
Just like any new piece of tech, once Dalton's theory was out there, other scientists immediately started stress testing it, and pretty soon, they started finding bugs. Little discoveries started popping up that just didn't quite fit with that simple, solid marble model. The bug reports were officially rolling in. And here's the first huge crack in the theory. Dalton was certain you couldn't split an atom. But then, whoops, scientists discovered that the atom wasn't a solid ball at all. It was actually made of even smaller things. You had positive protons, neutral neutrons, and negative electrons buzzing around. All of a sudden, the indivisible atom had been, well, divided. That was bug report number 1. But it didn't stop there. Next up, Dalton's idea that all atoms of one element were perfect clones of each other. Take chlorine, for example. He thought every single chlorine atom was identical. But then scientists found isotopes. Turns out, you can have 2 atoms of chlorine that have different weights because they have a different number of neutrons. They're both still chlorine, for sure, but they're not identical twins. Another bug found.
And this was the real game changer, the final blow to the old model. Dalton thought atoms were forever. You couldn't destroy them or change them. But then scientists figured out how to do something that sounded like straight-up magic. They could actually change one element into a completely different one in the lab. This proved atoms were not indestructible. It was definitely time for a major system upgrade.
so with all these discoveries piling up, Dalton's simple theory just couldn't keep up anymore. So, building on the work of so many scientists, a new theory was born, the modern atomic theory. And this wasn't just a small patch. This was a complete overhaul of the entire system.
This new model totally rewrote the rules. First, it acknowledges, yes, atoms are made of smaller parts. It also redefines the atom's job description. It's the smallest particle that gets involved in a chemical reaction. And it confirms that atoms are absolutely not indestructible. In fact, their mass can be converted right into pure energy, thanks to Einstein's famous equation, E equals mc squared. This is the powerful model we still use today.
Okay, so now we have this amazing, complex, new picture of the atom. But it creates a massive practical problem. Atoms are ridiculously, unbelievably, mind-bogglingly small. You can't just pick one up and pop it on a scale. So how in the world are you supposed to weigh one?
Well, first, let's make the problem a little easier. When we talk about how heavy an atom is, we're really just talking about its protons and neutrons. The electrons are so incredibly light by comparison, they barely add anything to the total weight. It's like weighing a bowling ball with and without a little speck of dust on it. The dust just doesn't matter much. So the real challenge is, how do you weigh the nucleus?
Scientists came up with a really clever workaround. They said, forget about grams or pounds, that's useless here. Instead, they just invented a whole new unit designed specifically for this job, the atomic mass unit, or AMU for short. And they defined it in a super specific way. 1 AMU is exactly 1/12 of the mass of a single atom of carbon-12.
Now, just inventing a unit isn't enough. For this to work, the entire world of science needed to agree on one single, stable, reliable atom to be the universal measuring stick, right? It's like if we all agreed to measure things in feet, but my foot is a size 9 and your foot is a size 12, none of our measurements would ever line up. We needed a standard.
And it actually took them a few tries to get it right. At first, they tried using hydrogen because it's the lightest, but that turned out to be a bit inconsistent. Then they switched over to oxygen for a while. But finally, everyone agreed on the perfect candidate, a super stable and common version of carbon called carbon-12. That became our universal gold standard for atomic weight.
And this brings us to the most important concept of all, relative atomic mass. The key word here is relative. We never actually weigh a single atom in grams. We can't. Instead, all we do is measure how heavy it is compared to our standard, that little 1/12 slice of a carbon-12 atom.
Let me put it this way. Imagine you're trying to weigh a single grain of sand. It's impossible with a regular scale, right? But what you could do is see how many grains of sand it takes to balance out something you can weigh, like an apple. In the world of atoms, carbon-12 is our standard apple, and all the other elements are the grains of sand that we're comparing it to.
And this is what it looks like when you put it all together. Hydrogen has a relative atomic mass of about 1, which means it's about as heavy as that 1/12 slice of our carbon-12 apple. Carbon, of course, is our standard, so it's 12. Oxygen is about 16 times heavier than that slice, and sodium is about 23 times heavier. It's a really elegant system for working with these impossibly tiny particles. So there you have it. We've gone from a simple, solid marble to a complex model buzzing with tiny particles. And we even figured out a genius way to weigh the unweighable. This knowledge is the foundation for pretty much all of modern chemistry and physics. Which leaves us with one last, really exciting question. Now that we finally understand the building blocks of our universe, what can we build with them?